Hi everyone, let's solve another conservation of energy problem. What should be the spring constant K of a spring designed to bring a 1200 kilogram car to rest from a speed of 95 kilometer per hour so that the occupant undergo a maximum acceleration of 4.0 gravity. So that's the acceleration. So here's a picture. The car is moving toward the spring, and then it's gonna press our spring. So there is a energy conversion from kinetic energy to spring potential energy. So you gotta remember the Hooke's law. The force of the spring maximum will be negative kx. That's because the spring is acting against the motion of the car, so we have a minus here. So going back to the question, I wrote down all the given variables. We have a car mass, we have an initial velocity of the car. Now they gave us in kilometer per hour, so we have to convert it into meter per second, the SI unit. And then the final velocity of the car, due to the spring stopping it, will be 0 meter per second. And the maximum acceleration we want is 4g, 4 times the gravity constant. And ultimately our goal is to find the spring constant that can accommodate our maximum acceleration. So conservation of energy is the key here. So we'll start with kinetic energy initial, and then the potential energy initial. This is a spring, by the way. There is no gravitational change in terms of height, and we'll disregard that. And the kinetic energy of the final of the car, and then the potential energy of the spring at the final. So I drew the picture here that the car is about to collide or is about to press the spring. At that moment, we'll call the initial. At that moment, the potential energy of the spring will go 0. The kinetic energy of the car, when the spring is pressed at the maximum displacement, that will go 0. So we write the kinetic energy of the car 1/2 mv naught squared, and then the potential energy of the spring 1/2 k delta x squared. The delta x in this frame will be positive because we'll align it with the direction of the car. I'm gonna circle the unknown variable we want, but we have a problem. We know the mass, we know the initial velocity of the car, but we do not know the displacement of the spring pressed. So what we need is a Hooke's law that we mentioned earlier, and let's elaborate that. At the maximum spring, you're gonna have negative kx, and the force that undergoes is a mass times the maximum acceleration. Now it's going opposite direction, so we now have to also plug it in negative 4.0 g, and we have a negative kx. We look for the technically delta x. We're gonna look for the delta x and just divide each side by negative k, the spring constant. You get negative 4.0 mg divided by negative k. The negative cancel out, you have 4.0 mg over k. we're gonna substitute that into where the delta x is. And let's just cancel out the 1/2 here to make our algebra easier. So we get 1 mv0 squared equals k, what we want, and then 4.0 mg over k, and that has to be over squared. We can square it right now, make it 16.0. Oh, actually, it's 2 sig fig. We'll just write the 16. M squared g squared over k squared, and we have another k here. mv0 squared. Cancel out the k, and then we're gonna push the k by cross multiplying it to the upper left corner. And then we'll push down the mv0 squared to the opposite lower bottom corner. So we get 16m squared g squared over mv0 squared. And notice how the mass can also cancel out partially here. So 16m g squared over v0 squared. We know the mass of the car is 1200 kilogram, and then the gravity constant is always positive 9.8 meter per second squared, divided by the initial velocity of the car, which we earlier calculated as 26.4 meter per second. And don't forget to square that. Using my calculator, I get, oh, I forgot to square there, and divided by 26.4 squared, I got 26, I don't know if you guys can see it, 2645. Newton per meter. That's the standard unit for the spring constant. And finally, we gotta double check our sig fig. We do not have any addition or subtraction, just multiplication here and division, of course. We have 2 sig fig, 2 sig fig. Well, this should have been actually 2 sig fig as well. Here's my guard digit. So we have to round up at the hundredth digit. You may write in scientific notation if you want, but you can also do like this. The 2 zeros here do not count as sig fig. And that's the answer.